Today's problem is graph diameter. Difficulty is medium, accuracy it's very high. Submissions 3,000. I guess this must be a fairly new problem. That is a low number of submissions. Either that or just people are just not interested in graph diameters. You are given an undirected connected graph with V vertices numbered from 0 to V minus 1 and E edges represented as a 2D array edges. Each element edges at I equals U and V represents an undirected edge between vertex U and vertex V. Find the diameter of the graph. What is the diameter of a graph? Diameter of a graph, sometimes called the width, is the number of edges on the longest path between two vertices in the graph. Note, graph does not contain any cycle. Okay. An example, V equals 6, E equals 5. That's actually not an input, the number of edges, but it's okay. We don't need that. Edges. The input is a 2D array. It's an array of two-element integer arrays. All of the edges. So there's an edge from 0 to 1, from 0 to 4, from 1 to 3, etc. All right. I'm not sure if I've heard of a graph diameter before. I mean, a graph doesn't necessarily have a diameter. But in this case, because the graph is, one, connected, and graphs don't have to be connected. I mean, for example, this graph here, if we just took out this edge between 1 and 3, that's still a graph. It's just that vertex 3 isn't connected to anything. The other thing here is that graphs are not going to contain any cycles. So if you have a graph, a connected graph with no cycles, that is actually a tree. Now, we can calculate the diameter of a tree. One way to do that is to calculate the longest path that passes through each of the nodes, and then take the biggest one. It's not the most efficient way of doing this. Let's see. What are the constraints here? Number of vertices is between 2 and 10 to the 5th, 100,000 inclusive. Number of edges is between 1 and V minus 1 inclusive. The vertices, and this is just, well, I mean, this follows from everything that we've been told already, that the vertices will be between 0 and V, not including V. We only have vertices from 0 to V minus 1. Expected complexities, O of n. All right. Auxiliary space, also O of n. So that makes sense. We're going to use a Q to do a breadth first search, so that's the auxiliary space. Graph. Depth first search. Data structures. Depth first search doesn't seem to me like the best way to do this problem. The depth first search. See, that sounds like you're going to go through every node and find the longest path. But there is a property of trees that would help us do this, and that is that we can pick any node in a tree and find the length of the paths from that node to every other node. And whichever path is the longest, we take the endpoint of that path and find the length of paths to every other node. And that longest length is going to be the diameter of the tree. I don't have a proof of that, but any node in a tree, the furthest node from that node will be an endpoint of the diameter. So, I mean, we can look at some examples here. Here is 0. The longest path from 0 is to 5. That is a length of 3. So that means we take 5 and we find the longest paths. The longest path from 5 is 4. Okay? That is a length of 4, and that's the answer. You could pick another one. Pick 2. What's the longest, what's the furthest node from 2? 1, 2, 3. It's 4. So 4 is an endpoint of the longest, of the diameter. So we go 1, 2, 3, 4. That's it. But if we pick 3, now we've got a tie. 1, 2, 3. 1, 2, 3. We have 4 and 5. But again, those are the endpoints of the diameter. So we can just take 2 iterations through the tree. Pick any node, find the longest path from that node to another node. Whatever that node is, find the longest path from that node to another node. That's the diameter. Let's look at this one. Actually, there's multiple possible longest paths here. Let's say we pick 1, 2, 3, 1, 2, 3. I'm trying to pick one here. That's 1, 2, 1, 2, 1, 2. Okay, let's pick 3. What is the farthest node from 3? So we have 0, 2, 2. Okay, 2 is a length of 2. 6 is a length of 2. 4 is a length of 2. Doesn't really matter which of those we pick. If we pick the 2, what we're going to find is the longest path from 2 to another node is 0, 3, 1, 6. That's what they list here as the longest path. Well, that's one of the longest paths, but we could go from 3. I mean, 6 is also one of the nodes furthest from 3. And if we picked 6, we're going to do the same thing in reverse. We're going to go from 6, 1, 3, 0, 2. What if we picked 4? Well, from 4, we would go to 0, 3, 1, and 6. Again, it's a length of 4. 2 iterations through the tree. All right. Let's take a look at this. Diameter graph. I did set up a graph data structure. Now, if you're going to go to an interview where you think it's possible that someone will ask you a question about graphs, you're going to want to know how to set up a basic graph data structure. You can see that. Well, we'll look at it a little bit, but one thing is this input, a 2D array of edges. It's really not ideal as far as figuring out what, pick a node. Now, what other nodes are adjacent to that node? So if we have edges, let's say, coming in like this, and we wanted to say, well, what nodes are adjacent to, well, let's start with something easy. What nodes are adjacent to 0? Well, it's actually not that easy because we don't know that the nodes are ordered like this, but we can see that 0 is adjacent to 2, it's adjacent to 4, it's adjacent to 3. Okay, what nodes are adjacent to 1? See, the node that you're looking for doesn't even have to be the first node. Now, 1 is adjacent to 3 and 6, but to find that out, with this data structure, you would have to look at this and say, okay, 1 is adjacent to 3, even though it's the second node in the pair. 1 is also adjacent to 6, although it's the first node in the pair. So I think one way or another, you're going to want to get the edges into a more amenable data structure. So here's what we can do. We can take graph, we can pass in the number of vertices, we can pass in the edges. And how do we construct the graph? Okay, so we have the number of vertices. I'm sorry, that's the breadth first. The graph, we pass in, here's the constructor for that. We are going to have class variables here. One is for the number of vertices, and one is for the adjacency list. All right, so this is a list of lists, meaning what we're going to convert it to is a list, and it could be an array of lists, I suppose, but we're going to do it as a list of lists. So we know that we have V vertices. So to access the adjacent nodes, we would like to be able to use V, our vertex, as an index into this list. And when we index into the list, we're going to be able to obtain an integer list of all the adjacent nodes. Okay, so let's see what's happening here. V comes in, we set the class variable. We create an array list and initialize it. It's going to have a length of V, because that's the number of vertices. And we're going to add an empty array list. So it's initialized, and then we can go through the edges. Wait a second. Now, I'm not sure that's what I want to do. Hang on. Sorry. Yeah, that is what I want to do. So for each edge, we're going to call add edge. We'll pass in the first vertex, we'll pass in the second vertex. And what add edge does is it adds an edge in both directions. So when we have something like, this 3, 1, what we add is that 1 is adjacent to 3 and 3 is adjacent to 1 because it's an undirected graph. And then we have an ADJ method, and that returns the adjacency list. It returns an iterable of all of the vertices that are adjacent to the input vertex. All right. All right, let's go back up and look at the main routine again. I'm going to scoot this over so everything is visible. Okay, so we'll come in, we'll create the graph. Again, you don't have to create the graph, but you do want to get, you really want to get either an array of lists or a list of lists, because trying to find adjacent nodes in a 2D array of edges is not what you want to do. So, all right, find a farthest node from an arbitrary starting node. I don't know, might as well start at 0. We're guaranteed to have a node 0. So we'll call a breadth first search, pass the graph, pass the node. Now the breadth first search returns an array of size V containing the distances of each node from the starting node. Let's take a look at the breadth first search. So what comes in here is G and a start node. we've got the number of vertices. We create a distances array of size v, fill it up with negative ones. Now, the negative one is an indicator that we haven't processed that node yet. We need a queue for the breadth first search. We put the start node in the queue, and we set the distances, distances array at the index of the start node to 0. Start node has a distance of 0 from itself. All right, now while the queue is not empty, we will dequeue the first element. First time through, it's the start node, and what we'll do is for every vertex that's adjacent to the start node, if it hasn't been processed yet, then we will set v to distances from the start node plus 1. And then we will queue that vertex to continue the breadth first search. Eventually, how would that work in practice, really? I mean, let's take a look at this. If we start out with node 0, and it has a distance from itself of 0, then we would queue the adjacent nodes. Queue the 2, queue the 4, queue the 3. We would well, actually, before we do that, we would set their distances. Okay, it's the adjacent node plus 1, so 0 plus 1. So 2 is a distance of 1, 4 is a distance of 1, 3 is a distance of 1. We queue all those. There's nothing to do with the 2 or the 4 because they are not adjacent to anything except the 0, but the 3 does have a couple of adjacent nodes. So 3 is a distance of 1, and the adjacent nodes would be set to the distance of 3 plus 1. So the distance to the 5 node would be 2, the distance to the 1 node would be 2, and we would queue those. There's nothing to do with the 5 node, it's not adjacent to anything, but 1 is adjacent to 6. So let's see, 1 is set to a distance of 2, and then we would set 6 to a distance of 3. Okay, so that's our first pass through the breadth first search to find the furthest node from some arbitrary node which we selected as 0. Now when we go through this a second time, we're trying to find the furthest node from 6, and actually there's a couple of them. It's a tie. You go 1, 2, 3, 4, or you could go 1, 2, 3, 4. You get to the 4 or the 2, but in any case the correct answer is 4. Let's see. Okay, so that's the breadth first search. Again, kind of circling back to the main routine, we have found the maximum distance from the starting node, and we have found what node is the maximum distance from the starting node, and so that is farthest node 1 is the node that we use for the second breadth first search. So breadth first search, pass in the graph, pass in farthest node, initialize max dist, and result 2 comes back with an array of distances. The distance of each node from, and in our example here it would be node 6, but the distance of each node from what we found as the farthest node from the first breadth first search. Okay, so initialize max dist to -1. Take every distance in result and find the biggest one, and that's the answer. This is a little different from this, although we want to do the same thing. We have to do this loop in this way because we not only need to know what is the maximum distance, but we need to know what node is at the maximum distance. In this case, we don't care about what the node is, we just care about the distance. So that's it. We should try and run this. And all right, let's see. Anything else to say about this? I mean, just to review a couple of points here. They present this as graph diameter. Now, a graph, as I said, it doesn't necessarily have a diameter. A tree has a diameter, and a graph that is both connected and does not contain any cycle is, in fact, a tree. So when they suggest depth first search here, it sort of sounds like they're suggesting that you find the longest path passing through each of the nodes and take the longest one as the diameter. But again, there is a property, excuse me, of trees where you can pick an arbitrary node in a tree, find the furthest node from that tree, and it has to be an endpoint. It will turn out that it has to be an endpoint of the diameter. So then you can use that node, find the longest path from that node, and that will give you the diameter. All right. That is it. And thanks for watching. Please go ahead and like the video. You can subscribe to the channel, and we'll see you next time.